So what happens if you run into an argument that involves a for all or there exists kind of statement? Well, then how do you figure out if that argument is valid or not? That means we need to consider inference rules for quantifiers, which is contained in this section of Rosen. So thankfully, it turns out that these inference rules for quantifiers are pretty simple. In fact, in this section of Rosen right here contains the following table. And this table right here gives us our inference rules that involve quantifiers right here. And you can see that they're actually pretty simple and pretty straightforward. And in fact, a lot of these can be verified simply by their definition. So for example, let's consider this very first one right here. And it comes with a fancy name. Universal instantiation right here. And it says if your hypothesis is for all x, p of x, that means you can conclude that p of c for any arbitrary c. And if we think about it, well, yeah, the definition of for all x, p of x, then of course, if you give me a particular x, like x equals c right here, then of course we can conclude that that is true. So in fact, this universal instantiation right here is simply by definition of what this universal quantifier right here is. And in fact, if we go through all the rest of these, and if you think about them for just half a second, you'll notice that actually these are all by definition, right? So if p of c for arbitrary c, well, that means for arbitrary c, that's all c. Well, that just means that for every x, p of x. So this here is going to be a valid inference rule. And same thing for existential quantifiers. There exists an x such that p of x, therefore we can conclude that p of c for some c. Well, yeah, that's the definition of our existential quantifier. And same thing over here, p of c for some c, therefore we can conclude there exists an x such that p of x. Well, yeah, that's the definition of our existential quantifier. So thankfully, these inference rules for quantifiers are rather straightforward. So let's go ahead and put it into action and look at an example. So considering this example, all humans are mortal. Socrates is a human, therefore Socrates is mortal. So we immediately recognize that we're going to have to use our inference rules with quantifiers because this argument involves a statement that contains an all right here. So as usual, to verify whether or not this is a valid argument, the first thing that we have to do is translate it into our logical symbols. So for this translation, let's go ahead and see what we can do. So first off, let's see here. All humans are mortal. So I need some sort of way to represent that something is a human. So let's go ahead and say h of x, which is my propositional function, is going to be defined as x is a human. And then I also have all humans are mortal right here. So I'm going to have some sort of propositional function representing that something is mortal. So let's go ahead and let M be my propositional function that X is mortal right here. And then lastly, I have this statement right here, Socrates is a human right here. So, well, we're talking about Socrates, and so Socrates is a human, so I'm going to let S represent Socrates as an individual here. And so with this translation right here, let's go ahead and convert this English statement over here into something that looks more like an argument in tabular form. So translating this, we would then get the following. All humans are mortal. So for every human, they are mortal. For every X, if X is a human, then they are mortal right here. Then it also tells us Socrates is a human, so I know that H of S is a true statement right here. These are my hypotheses right here. All humans are mortal, Socrates is a human. And the claim, the conclusion is therefore Socrates is mortal. So what they want to claim is Socrates is mortal right here. So let's go ahead and see if we can figure out if this is a valid argument. Well, first off, if I look at my inference rules right here, and I look at this universal instantiation right here, since I have H of S, and for every X, H of X implies M of X, if I apply this rule right here, that means that I could translate this into the following. So how did I use universal instantiation right here? Well, I know that for all of X, this statement right here is true. And I also know H of S is true, right? Because these are my hypotheses, and I'm assuming that these are true right here, and I'm trying to show that my conclusion right here is true by those hypotheses. So since H of S is a particular instance of it, since I know that this universal quantifier is true for all X, I know I can conclude it's true for a particular one like S. So if I stick an S in here, it's going to be true. And you notice that that's all that I've done right here. I've stuck an S in here, and I know that that's going to be true. So I've used my universal instantiation to be able to translate this right here and say, well, this is basically the same argument as this. And then if we think about it, well, the way that these functional operators right here work is that this right here is just a statement, and that right there is just a statement, and this right here is just a statement. So all this is really saying is P implies Q, right? Because I could think about this as just a logical statement P. M of S, well, that's a Q, and then P, therefore Q. Yeah, we've seen that a bunch of times already, right? This is our old modus ponens, and this right here indeed is a valid argument. So in conclusion, our inference rules for quantifiers are relatively straightforward. If you see for all of X, you can plug in any individual variable right here and know that it's going to be true. That's this universal instantiation right here. If you see there exists an X, you know that it's true for some C, etc.